long-running tradition here at SGP, and all the talks will go online, and there's this nice sort of online archive of all these talks. I'm really happy to introduce our first speakers, Robin Walters from Northeastern. He's a professor there. Interestingly, I just found out, there's a lot of graphics folks in the room. He worked at Pixar, actually, before he went off to do his math PhD, which I thought was such an interesting connection. And his student John Park as well.
Thanks, John.
They've done some excellent work in equivariant neural networks, and they'll be telling us about.
Okay. All right, thank you for that great introduction. I'm really happy to be here. Thank you for coming right at the beginning of what, at a time that I used to consider too early to think deeply about math. As Edward mentioned, my path has been long and winding. So I was doing protein structure, and then I was doing computer graphics. And then I did pure math, and I studied representation theory, which is the formal study of systems of symmetry. And then I came to Northeastern, and then I started collaborating with people who were doing deep learning. And then we started to say, can we bring these things together? But the through-running thread has always been leveraging geometric structure. Okay. All right. So I see my work as addressing some of the sort of limitations of the current methods in machine learning. So, we're all aware of how powerful various machine learning models have gotten, right? But there are some hidden limitations that really start to emerge when you look, as we do, at certain engineering and scientific domains. So one is poor generalization. So models train very tightly to the training distribution that you give them. That's really fulfilling their purpose. That's what they're designed to do. But when we look at something like fluid mechanics or robotics, we often have some domain shift between the training data and the real data, and we want the model to be able to bridge that gap. And the current generation of models don't do that very well. You have to do something specific. The other thing is that the current success of large models is also predicated on giant data sets. So if you have enough data, you can scale the model and produce neural networks that perform very well. But there are lots of domains where data is expensive or scarce, right? So here I have the picture of these robots, right? This is somebody trying to train a robotic manipulation policy on actual robots. And in this case, the data is environmental interactions performed by a real robot in real time. And when the robot fails to pick something up and knocks it off the table, somebody, probably a graduate student, has to pick it up and put it back on the table. So we're not talking about billions of data samples here. That's not a reality, right? And so the other issue is physical inconsistency. So we're targeting applications, in science like climate or control systems where, these predictions have a big impact on people's lives. They're modeling physical systems, and hallucinations are a big problem in these domains. And so if we can leverage some sort of geometric or mathematical structure to improve the physical fidelity of these models, then that would improve the situation in these domains. Okay, so what is the problem to these limits of current machine learning technology? So I sort of see, this is my view, is that there's sort of three big strategies that people pursue these days. So one is what we call inductive bias or strong priors. This is saying instead of doing everything in a purely data-driven approach, I'm going to bring in some physics or mathematical structure, so create some sort of hybrid model that leverages non-learned principles to improve performance, and that can be very effective. Another is data augmentation. So that's the idea that if I don't have enough data, make more data somehow, right? Either by adding noise to it, or maybe training a generative model whose whole purpose is to produce data for other models to learn. And the last is semi-supervised pre-training. So this is just this, these days you hear a lot about foundation models. So this is some idea that instead of narrowly training on a task, if I don't have enough data for what I want to do, I can sort of train a model on a larger corpus of data, and the sort of insights and like essentially the features that I learn from that larger structure will help aid the learning in the specific place. So all of these can help cope with situations where I don't have enough data or I want better generalization. And I drew them as a Venn diagram because I don't see them as mutually exclusive. Even though the people who work on them might see themselves as competitors, these methods can work together, and in fact, there can be synergies between them. Now, most of this talk is on this approach. This is how our methodology favors, is we try to think about leveraging mathematical or geometric structure in the problem as a prior for designing neural networks that are going to be more efficient. And specifically, the prior we use is symmetry. So the specific way that we have geometry enter the problem is by trying to leverage the system symmetry and get it into the problem. So this slide, I just wanted to flash this slide. This beautiful drawing is from Michael Bronstein's keynote talk at ICML a couple years ago. And they've got there's a paper there that's like a 150-page tutorial that you can look at called Geometric Deep Learning, Grids, Groups, Graphs, Geodesics, and Gauges, right? And they've sort of outlined what they call an Erlangen program for deep learning, where they suggest that there's like a highly philosophical approach to deep learning that says that the first thing you do when you design a neural network is look at the geometry of the data. Like what is, and not in a deep topological data analysis sense, but just is my data an image? That means it's a signal over a grid or a space, right? Or is it a graph, right? Then those things should inform the way the neural network works. And so in other words, the model, this is a philosophy of non-data agnostic architecture design, right? But of this I think they used the word model zoo. From this model zoo, what we're focusing on is symmetry. So that's the structure that we want to lift. So here's my simple cheat sheet for here's what you do to get symmetry into your neural network. So first we look at a problem, and later I'll show all the different domains we've collaborated. But we talk to somebody. The first people we talked to were some fluid dynamics people at Lawrence Berkeley. We said, okay, what's the symmetry in your problem, right? And they said, okay, here are the symmetries. And we said, okay, now let's go and we're going to design neural networks that build those symmetries in. Right? So we designed specific neural networks that were symmetric type neural networks, and then we trained those neural networks on data. And the neural networks that have the symmetry in them, they outperform the neural networks that don't. Okay. So now a little background. I talked to different audiences. Probably this audience. Who knows what symmetry groups are? 50% maybe. Or maybe 100%, but some of you didn't want to raise your hand. Okay, so different people know different things. But typically when I talk to a straight machine learning audience, a lot of them don't know about the abstract algebra. But computer graphics people maybe more. Okay, so here's the cyclic group. So this is a abstract symmetry template, I like to think of it as, right? And that's the entire data of it. So it's a set with 4 elements, and it has a multiplicative structure, which is that if I multiply r by itself 4 times, I get r to the 4th. And that's equal to 1. So this is like z mod 4z under addition, isomorphic, right? So this is the cyclic group of order 4, but that's the complete data of it. So it records the abstract structure of a symmetry, but it's just a template. So the way that this template actually becomes something that you would have recognized as symmetry when you were in kindergarten is through a representation. So representation is a homomorphism from this group to a set of invertible matrices of a given size. So what that's saying is I take each of these 4 elements and I map them to, in this case, I'm looking at 2x2 matrices. So I map each of these to a 2x2 matrix such that when I multiply the matrices, I get this structure. Okay, which means that when I multiply the matrix that I send R to by itself 4 times, I should go back to being the identity matrix. And so here, this is, of course, a 90-degree rotation matrix, and if I multiply it by itself 4 times, obviously I'm going to get the identity. So rotation becomes a concrete representation of that abstract symmetry template. Okay, but what's going to matter in a moment when I talk about equivariant neural networks is that the same group, the same abstract symmetry type, can have different representations. And they're all, in some sense, equally natural from the point of view of this group. So here's another representation. So this is a 4-dimensional representation of the cyclic group of order 4. So what's another symmetry that has the property that when I do it 4 times, I get back to where I started? Cyclically permuting 4 things. So if I cyclically permute 4 things, if I do that 4 times, they're going to come back to where they are. So this is a cyclic permutation matrix. And if you want to, if you love multiplying matrices, then multiply it by itself 4 times, and it'll get back to the identity, right? Okay. All right. So that's groups and representations. Okay. So this is just a math concept, but this is going to bridge us back to how does this have anything to do with neural networks, right? So when you have a group and you have representations, you can talk about a function being equivariant with respect to that representation. Okay, so like everyone knows the word invariant. We talk about all that a lot, right? But equivariant, right? Invariant means it didn't change. It's invariant. It didn't change. But equivariant means 2 things changed the same way. Okay, so in this case, what we're showing is that if the input to this function x is changed in some way by some group element g, and that row in, right? That row in of g is specifying that this group element g could it be acting on the input and output space by different representations, like we just saw, okay? But it's saying that if you have the same group element acting on the input, then that effect should be the same on the output side. So if I transform the input and then apply the function, it's the same thing as applying the function and then on the output. So here's like some pictures. So here the symmetry is translation. The function on the left is classification. So that's an image. It's an image of a rose, and so the label is invariant under translation. If I translate the image, the output shouldn't change. And on the right is an equivariant task. So that's segmentation, where every pixel gets labeled with a class, like sand or tiger, right? And the segmentation task is translation equivariant, which is to say that if I were to shift the input image in some way and then segment it, that's the same thing as if I first segmented it and then shifted the image. Okay? So equivariance helps us realize that some task, like classification or segmentation, has some interaction with some symmetry. We recognize that a priori. There's no neural networks on this slide, right? This is about the ground truth. Okay. Okay, and here's rotations. So here's digit classification. This is actually kind of a strange example of this, but you always have to put MNIST in everything. But if I rotate the 5 a small amount, it's still a 5, right? So that's an invariant classification task. Usually someone objects at this point and tells me that if I were to rotate like a 6 180 degrees, then it becomes a 9. So that means digit classification is not an invariant task. And that's like somewhat true, but it actually turns out that if you rotate all of the digits in MNIST and train a classifier on the original labels, you can still get very good accuracy. So what that tells you is that like as far as handwritten digits are concerned, a 180-degree rotated 6 is different than how people write 9. And those are actually still distinct things. From like certain font point, like you could choose a font that actually is rotationally symmetric, and then that would be a different problem. Okay, and then segmentation, like our previous example, is also rotationally equivariant, right? I can rotate and segment, or then segment and rotate. Okay, so that leads us to the following question. So now we've sort of done the first step, which is looked at the tasks and identified the symmetries. Now the question is, how do I design a neural network architecture, or model class, as we say, that embeds these symmetries into the structure of the architecture, right? And you've probably like already thought of some examples of this, like when I was doing the translation case, right? Which is a convolutional neural network, or at least a convolutional layer. There's a bunch of asterisks. So in which with zero padding, in which the signal is centered and the shifts don't move the signal out of the center, and the convolution has no dilation or stride, is shift equivariant to pixel shifts. So the basic, most vanilla structure of a convolutional neural network is shift equivariant to pixel shifts. Okay, so that's already an example. And another example is GNNs. So graph neural networks, if you've heard of them, right? They operate on data that lives on a graph, and those are permutation equivariant, right? So that that's a little subtle, I won't get into it, but essentially has to do with the fact that you can't really like tell a neural network. It's hard to tell a neural network about a graph without ordering the nodes. That usually ends up happening at some point because neural networks take tensors. Tensors have order. And the problem is that ordering was a choice, and the choice shouldn't actually affect the answer. And so the permutation equivariance refers to that ordering. OK. Because this is a mixed audience, so for people who don't know, so let's talk about how to build a neural network and then what it means to put equivariance into it. So here is an input image, and I've simplified this classification task to be about labeling it as a cat or a dog. So we want to build a function with trainable parameters that takes that image as input and tells us whether it's a cat or dog. OK, so the first step is to vectorize. So this image is 3 by 128 by 128. So it's just a giant tensor. I can maintain various aspects. OK, and then now that it's a vector, right, I can now pass it through a neural network. And while most people know, I'll just say, the basic template of a neural network is actually an extremely simple thing. I take this vector and I multiply it by a matrix, M1. Okay? That matrix has input dimension equal to whatever the dimension, 3 times 128 times 128. But the output I choose, it's called a hyperparameter. It's the latent dimension. Then I apply a nonlinearity. So this is the nonlinearity that's usually applied element-wise over the vector, something like sigmoid or tan h, or a function that simply takes all the negative numbers and zeros them, or takes the positive numbers and leaves them the same. And then I multiply the output by another matrix, moving to another dimension, and so on and so forth, as many layers as I want until I get to an output. And that output will be, in this case, a 2-dimensional vector. And it gives me the probability that the class is either dog or cat. So that's the model, right? And that's what a neural network is, basically. And the way I think, the originally inspiration for these, they called them artificial neural networks. And the idea was somehow that these matrices were modeling like the connection of neurons in your brain. And these nonlinearities sort of model the fact that there's like, when a bunch of neurons like send an electrical signal to another neuron, if there's enough, then that next neuron will fire. And so these activation functions are supposed to be modeling this like activation threshold. They're often called activations. I think of it differently. I think of it as linear regression is like the best way to fit functions, except that it doesn't fit all functions well. So if you want to fit more complicated functions that are not linear, you need to throw some nonlinearities in there. So that's what this is. And so this turns out to be almost absolutely the simplest thing you can do besides just multiplying a bunch of matrices together that gets you what's called universal approximation property, which means I can now model any function, not just linear functions. So I just think of this as like linear regression plus plus. OK, I should have shown you these pictures. OK, all right. And so now the problem, of course, is like, sure, I explained to you that you could multiply a bunch of matrices together, but I didn't, like, those are just matrices. Like, who says what the values in the matrices should be? And the answer is training. So you randomly initialize the values in the matrices. Then you start passing inputs through the networks, right? Then you compute the error of the output. So at the beginning, the output is terrible, right? But you can differentiate these models, and you could say, what tweaks to all the weights would have given me something more like the correct answer on that example you just saw, OK? So this is called computing the gradient. And then you do what's called gradient descent, which means you do an update. So then you tweak all of the entries and all of the matrices such that the answer on that example you just saw, or that batch of examples maybe, all would have been better. And then you do it over and over again. And it takes many steps and much data. But I feel very confident in saying this. Amazingly, right, this process of continually tweaking the weights, sort of data point by data point, will, in many cases, ultimately get you to values in those matrices where that model straight through actually gives you good answers on the data. So this is the picture. And so there's like the true function over here, right? And where I lost the mouse. That's OK. There's the true function over here, and here's the class of all the different like values of the entries of the matrices, which we call parameters. And eventually, given enough time, we'll get pretty close to that true function. OK. I'm gonna skip this for time, and we'll just look at it like this. OK, so the question now is, now you saw what equivariance is, And you also saw like what I draw as a picture of a neural network. So the question is, how do we make this network equivariant? Okay. The idea is we just observed that like let's take segmentation. The segmentation problem is equivariant, right? We know that a priori. We know the function we're trying to learn is equivariant. So if I can make the neural network equivariant, even before we start training it, that's that process of gradient descent on data, then that's a huge leg up in terms of learning this problem, right? So how would I do it? So here's the same neural network I showed you before, okay? But I've added, the new part is this like G at the bottom. So that's the symmetry group, right? And now I've drawn these row for representation. This is how the group G acts on the input space and output space, right? That was given by the problem. Like an image rotates however an image rotates. So that's what the rotation group action is. And then these row I are choices for how should the symmetry group act on the latent spaces. So I think of that as like, well, mostly a really cool thing, right? Because like, it's sort of saying that these latent spaces, like R to the 128, it's just some like, supposed to be some like activation of neurons that represents some deep feature of my input, right? I'm choosing ahead of time how that should transform under some sort of like change of coordinates. So I'm assigning it sort of a geometric meaning, not like a specific one. I don't know what the neural network will sort of choose to put there as I train it. But I'm saying, oh, I actually want you to put like some invariant scalars, some vectors, some things that transform the way tensors are. Maybe I can use this to specify various like amounts of data in different Fourier spaces. So like I could like focus on high or low frequencies. That is all determined by what choice of representation I pick. So I'm sort of like geometrically typing my latent spaces. Okay, and so in order to build an equivariant neural network, you need to, so there's a fact. So if you have two functions that are both equivariant, if I compose them, that composed function is equivariant. So here, a neural network is a composition of a bunch of functions, right? It's first a linear function that's multiplying by a matrix, then a nonlinear function, which is applying an activation to every entry of the vector, and I alternate. And at the end of the day, if I have a 16-layer network, I have composed 32 functions, one linear and nonlinear function for each layer, right? And so if I can make each of those functions, the linear layers and the nonlinear layers, equivariant, then composing them, my entire model will be equivariant. So now I've reduced the problem to two things, which is telling you what does it mean to have an equivariant matrix, and what does it mean to have an equivariant activation. So I'll do this example, and if you kind of get this example or work through it later, you'll basically have the idea. So we'll start with the linear layer. So let's look at this mapping. I've done this example. So we made D1, 2 and D2, 4. So those are laughably small latent dimensions for a neural network, but we'll pretend, okay? And so this matrix M2 is a 4x2 matrix. So there's got 8 entries, and it's mapping this space. And these are all trainable entries. And now I want it to commute with the action of C4. So we did the example group, the cyclic group of order 4. So let's use that. And let's say that we've chosen row 1 to be 90-degree rotation. So that's how we act on the R2. And we've chosen row 2 to be cyclic permutations of order 4. So we've chosen the way the cyclic group acts on these two spaces. And now the question is, which matrices M2 will intertwine this symmetry group action, or equivariant with respect to it? And here's the answer. And you can solve this. There's actually a linear problem to solve this, right? But if I had an unconstrained non-equivariant neural network, these would all be 8 independently variable parameters that could be trained, right? But because I'm saying that I want rotation before matrix multiplication to be the same thing as rotation after matrix multiplication, that constraint says that I have to have matrices of this type. So that 8-dimensional space shrinks to 2 dimensions, okay? And now when I train my neural network, it's actually very like, I don't know, it's pretty easy, like in PyTorch. I just instantiate A and B, these coefficients, as trainable parameters. Then I build that matrix out of them and multiply by that matrix. And then the training process will just update like the various entries of the matrix that are linked by the same parameter. So if A moves, it'll change 4 different entries in the matrix at once. And so now the picture that you have in your head, oh, so there's the computation you can sort of work out. But this matrix, whatever the values of A and B, will commute with the rotation action. And so the multiplying by R at the beginning of the network can be passed all the way through. So go ahead and you can do the if and only if you really get bored. OK. And then for the activation functions, I don't like to talk about this much because it's more boring, but the activation function, by the way, so finding the class of such things, the equivariant linear maps, those are called intertwiners, and that's like a big problem in representation theory. So that's the sort of thing representation theorists like to study. That often means the answer is usually in a textbook, so that makes your life easier. But the activations matter too. So, and it depends on the representation that you choose. So like in neural networks, choosing the activation is a somewhat important part of neural network design. And what I'm saying is that if you want equivariant neural networks, your choice of activation is constrained by the symmetry. So in the case of the cyclic permutation, like something like ReLU is fine. But in the case of the 90-degree rotation, if I take a vector and rotate it 90 degrees and then zero some of the entries, the negative entries, that doesn't commute with 90-degree rotation. So I need to think about an activation that will commute with rotation. So the answer is it's a nonlinearity that has to change the length but not the direction of a vector. OK, so this is my new picture, right? Remember, I have the space of all of the neural networks. I start randomly in this space, and I start moving towards my true function through training, right? And then I have the space of equivariant neural networks, which is the smaller constrained space. And the true function is equivariant, so it lives in that space. And so now I've shrunk my search problem to a smaller class that contains the point that I'm interested in, right? And this picture is bad because it makes it look smaller, but it's how I drew it. But you guys just actually saw what the true picture looks like, which is I moved from some 10 million dimensional space to some maybe 1 million dimensional space or 200,000 dimensional. I mean, you can compute the dimensional reduction of the problem. OK, so as you can imagine, the ability to build neural networks that incorporate symmetries from a domain is useful in a lot of domains. And these are specifically sort of geometric or physical domains where there is geometric structure to exploit. So we love working on physical dynamics problems. All of these are I'm not really an expert in any of these fields. And so each of these bullets represents a collaboration of my lab with some people who actually know about these things. And often a very fruitful story where they tell me about their domain and we discuss what symmetries are available. And then we build some neural networks to leverage them. OK, so I'll just talk. I have 12 more minutes, so I'll talk for 6 minutes each about 2 examples of this procedure. And then John, my student, will take over. OK, so this is a collaboration with Ray Wang. He was a postdoc here at MIT with Tess Schmidt, but he now I think he's working for GE Health as a researcher. And Rose Yu at UC San Diego. I was talking to someone from UCSD recently. OK, so the problem here is predicting. So this is sort of a video prediction problem, but we're looking at vector fields of some sort of flow, turbulent fluid flow. We look at, say, 15 past vector fields of the flow, and the goal is to predict the future of the flow, right? So this could be useful for weather prediction, right? Suppose I have wind fields, or I have the ocean current fields, and I want to predict the future of those fields. That's an important part of developing a climate model, right? So I want to be able to predict them. Or, for example, I want to design an airplane wing. So I want to build a fast simulator where I can run a lot of different types of airplane wings, and I can model the flow over the wing rapidly, right? OK. And the point is that if G is a transformation, like rotation or scaling, that preserves this system, then this whole thing will be equivariant. So in other words, if I take the, I guess I have a picture in a little bit. OK, so here's the Navier-Stokes equations. So these are the incompressible Navier-Stokes equations without an external force and no boundary conditions shown, right? So if V is a velocity field, these equations govern the time evolution of that velocity field. OK, what you can test if you like, and I didn't write it out, but I have before, like when I talk about this in a class. So you can test that these equations are invariant under a scaling law. So that's the scaling law I've put there. It's an anisotropic scaling law. So it says if you scale space up by a factor of lambda, and you scale time up by a factor of lambda squared, so it's a spatiotemporal scaling, and then that means that you're scaling velocity by 1 over lambda, then that will preserve these differential equations. So that becomes a scaling relationship within fluid dynamics, right? This is a very like special, well, it's not that special. It pervades a lot of like physics. It just derives from the Newtonian mechanics. But without this, like you couldn't build wind tunnels, right? Like I've always taken that for granted, but like you would just have to build full planes because there would be phenomena that occurred at scale that didn't occur at the smaller scale, right? Like. But fortunately, there's a scaling law that relates the dynamics. And as long as you know how to like relate the time and velocity dimensions, you can scale things up, right? I mean, I would suppose that, like, for example, paleontologists have no such like thing, right? Like there's like some square cube law effect. I don't know about, but like you couldn't build a tiny dinosaur to study dinosaurs. That just wouldn't be the same thing as the big dinosaur. So you just have to build a big dinosaur, right? So thank God. Okay, so now the question is, if I have that scaling law, that's a scaling law that fluid dynamics has. Now I want to train neural networks to learn fluid dynamics. Let's build that scaling law into the model. Okay, so for a quick like brush with it, what I'll show you is the example we talked about earlier of when symmetry, that we knew of when symmetry was in a neural network, was the case of CNNs. And this is the convolution. This is a 2D convolution. That's the workhorse of a CNN. Now, you can ask at a high level, just like quickly to understand, what makes a CNN equivariant to shifts? And the answer is that it has a kernel, which are the trainable weights of a CNN, and it merely applies that same kernel at every position on the input. So if you were to shift the input, the kernel would still get applied at all the same positions of the input. There's no input. The weights that I apply don't depend on the absolute position of the image. I just apply the same weights across the entire image. So now if I want to like leverage that philosophy, and that in this formula that's given by the sum. So the convolution is evaluated by summing over all positions of the input. So if I want to build something which is both shift and scale equivariant, I essentially have to take my kernel and not just shift it over all positions of the input, but I also have to scale the kernel over all positions of the input. And if I do that, I will build an operation. This is an example of a very general phenomenon called what's called a group convolution. So both CNNs and this thing that I'm showing you are examples of group convolutions. And this group convolution will be equivariant to the group that I'm considering. Okay. And there's a bunch of like details here, but I will skip over them for now. So here's kind of a pictorial representation of kind of what we're doing. Okay, and then I'm going to skip over how you do this for rotation, but it makes for very pretty pictures. I'm just going to tell you something about the results. So I'll just show you this slide. So what is the result? So if you take a neural network that knows about the symmetry of fluid and you train it on the fluid dynamics, then we can test the following generalization property. So I want you to look at the right one, the right graph here. So basically what we've done is we had a data set that was given to us by these really nice people at Lawrence Berkeley. And we trained our neural network to model the evolution of the fluid flows in this data set. And then what we did was we scaled the data. So the premise is, if you think that a neural network learns the physics, after studying like about 20 terabytes of fluid flow data, does it know the Navier-Stokes equations, right? Which is like, I don't know, 20 bytes of data, right? Like, then if you scale up the fluid, right, it should take those fluid dynamics and apply them, right? Well, this gray line is the error rate as we scale the fluid. So as we scale the data samples in our data set and test the model, the error shoots up, right? At the same time, if we take a model that we've built the scaling symmetry into and train it on the scaled data, that gives me the blue line. So we get some error because this is gridded data. So there's aliasing effects and resampling effects and loss of information and downscaling. So there's all sorts of stuff to do with the fact that it's images that I'm working with. But overall, the error remains quite low, right? So this, to me, this is great. This is what we want. And there's nothing like wrong. I'm not throwing any shade on neural networks. They're doing their job, which is fitting the distribution very narrowly. But that's not what we want in this situation. OK, great. OK, I'll just so that was one application. I want to talk about one more application before I turn things over to John. OK, so this is pose prediction from 2D images. So I like this. Yeah, this was an oral presentation at iClear last year with David, Andre, and Rob. So Rob is a roboticist. So this was motivated from really a robotics problem, which is people want to take robotics. They want to move from low-dimensional representations of the system they're working with to just images. The goal is, what if a robot can just learn with a camera mounted on the front, right? And so pose prediction, I mean, it's a fundamental problem in computer vision, is 3D interpretation from 2D images. But our specific motivation was from robotics. Could we look at a bunch of stuff and get a low-dimensional representation from it? OK, so here's the problem. So we give a natural image of some object. We want to pass it through the neural network. We want to get an element of SO3, so we want to get an orientation, right? So pick your favorite one, 3x3 matrix, or Euler angles or quaternions. Don't pick the quaternions. And then, OK, and this is a hard object, a hard task. In particular, there are lots of data sets for it, right? But it's a fundamentally ambiguous problem. If I take that bottle, its orientation is not defined as a single orientation, right? Because if I rotated the bottle, I can't tell without any distinct markings or labeling the atoms in the bottle what its exact orientation is. It's the best I can do is give you one circle, one SO2 subgroup with orientations. Also, depending on what I see of the object, I'm really obliged to report some amount of ambiguity. So this rotating mug with the Northeastern husky on it, right? When I can't see the handle and I can't see the husky, there's a range of values that I should return. OK, so here's our solution. So I like this because it kind of gives you a flavor of how flexible this kind of method can be, right? And I also think it's inspiring from a geometric perspective, because this problem is fundamentally about going from one kind of geometric signal, which is 2D images, to another kind of geometric signal, which is SO3 orientations over this Lie group manifold, right? And so I can't do the simple thing I did before in a CNN, where I just say it's images all the way through, right? We have to convert somewhere in between. So David had this pretty neat idea where he said, let's use a CNN at the beginning. So we'll take an image and we'll process it as an image, right? And in fact, that ResNet can be pre-trained on a large image, on a larger image corpus if you want. So that's an example of how the strategies in my Venn diagram overlap, right? And we end up with this feature map. And then at some point, we have to go to the 3D world, right? And so we will go onto a sphere. And we'll just map it using orthogonal projection. So we'll just map it onto one side of the sphere. And I mean, there are a lot of things you can do. And in fact, we have a follow-up work where we sort of use representation theory to sort of constrain the space of all possible mappings that have the correct SO3 to SO2 restriction. But in this first work, we just orthogonally projected. We said, this is an image. It's a view from one side. So when we enter the 3D world, we're projected onto one side. So now we have a spherical signal. So now we do convolutions over the S2 manifold, right? So we do spherical convolutions, which is like 2D convolution, but you can have a kernel on S2, and you can translate it all over S2. And then that gives us a signal in SO3. So now you're up in a 3-dimensional manifold. And now you do SO3 convolution, which is an example of group convolution that I haven't talked about that much. And then the output naturally, so this convolution, there's the orthogonal projection. And this convolution is naturally performed most, if you know the convolution theorem, it says that in Fourier space, convolution is element-wise multiplication. So the way you actually perform a convolution over SO3 is you use what are called spherical harmonics or coefficients of Wigner D matrices. So these, I'm going to say a bunch of words. These correspond to the irreducible representations of the SO3 group, and it's just like the Fourier space, where basically I can do a convolution very efficiently in this essential Fourier space. At the end of the day, I take some inverse Fourier transform. And when you inverse Fourier transform out of the Fourier space of SO3, what you get is exactly this kind of function. You get a heat map, like a signal, which assigns a real number to every rotation. So if we normalize that, that becomes a probability distribution over SO3, which is exactly the output type we want. So I'll just end on these results, right? So these are some pictures of the distribution the model is predicting over the orientations of these input images, right? And I think it's very beautiful. You can see that some things like this computer monitor are unambiguous, or the chair, but some things like the bus, it has 2 points, right? Because there's, in this case, the bus almost kind of has like a rotational or reflectional symmetry. I believe in that case, it's having trouble telling if that's the front or the back of the bus. Fair enough. And then in the case of this rotationally glass bottle, I get an output, which is exactly the kind I expected, this sort of rotation. OK. Oh, yeah, there's this. Here's this very beautiful, the solids and the sort of ambiguities that I expect from them. OK. I'm going to hand it over to John.
Actually, I thought,
yeah?
given maybe it would be good just for a second, like before you transition off, like, does anyone have any questions?
Sure, yeah.
Yeah.
So on the scaling model, it seemed like you built scaling invariance into the model.
Yes.
And then your test that it worked was look at scaling invariant.
More or less, yeah. There were many tests, but that's sort of the one that I'm showing, yeah.
Are there other properties of Navier-Stokes that come out more naturally from that because you held it scaling invariant?
Yeah, so you wanted to see the other slide that I skipped.
Would you mind repeating the question into the microphone because we're recording the chat?
Sure, yeah. I think the question was really like, the result I showed was the expected. Well, for my model, it was the expected one. I built scaling in, and I succeeded because it scaled, right? But are there other properties I get? Maybe, like, I don't know if I want to use the word emergent, but like, I told it about some stuff about the symmetry group of Navier-Stokes. Do I get other benefits from that? So here's some pictures. So this is tested on ocean flow. I'll just zero in on one number here, or some numbers. So this, again, coming from our great collaborators, they were like, look, it's ridiculous to look at the RMSE of fluid flows. People look at the energy spectrum. That means the amount of energy contained in the fluid flow at different scales, how much energy is in large versus sort of small eddies. That's how we test the fidelity of our simulators. So what we did was we compared the energy spectrum of the predictions of our model that incorporated the symmetries of the Navier-Stokes equation to the energy spectra of the true, right, and to the energy spectra of baselines. Right? And the result is things like this. So for a model that incorporates rotational symmetries, the energy spectrum is dramatically more realistic. So that's, I think, kind of an answer to your question. All right.
All right. So hello, my name is John Park. I'm a PhD student working with Robin. And so I'll just talk about a couple of works that I've did. And so it's about basically, it's about more work on how to apply equivariant networks in situations where, like, they can't be applied directly, and it's kind of like extending the applicability of equivariant neural networks. So first, I'll present our work on learning group actions with symmetric embedding networks, or SENs, and this work tackles a scenario where you know the symmetry group, but you don't know the group actions or how it acts on the input space specifically. And this work was done with Andre, Lin Feng, and Yeon, Lundemit, and Robin, of course, and presented at ICML 2022. Yeah. All right, so as explained previously, there can be cases where it's difficult to characterize the symmetry, how the symmetry acts on the input data, or the group action is unknown. So if we look at the figure on the left, so it's easy to characterize a group action for the mness digit, because it's a simple rotation in 2D pixel space, and you just apply the same rotation matrix to all of the pixels. But however, for the car image on the right, the group action is not so straightforward because it's like a 3D rotation projected onto a 2D image, and it's basically an out-of-plane rotation. So now the group action would need to be computed for possibly every pixel, and so we would end up basically with a large number of matrices, and we'd have to compute them individually. So however, if we can learn like a top-down view of the car as like some sort of low dimensional representation, then now we can simply get a very simple transformation. Now, in other words, basically some group actions are easier to compute in some spaces than others. And in this work, we propose symmetric embedding networks to learn such embeddings. Yeah, actually, I think for my talk, I'll try to focus on the concepts more rather than the details. So yeah, the ideas, I guess. All right, so to learn the symmetric embeddings from data, we pair the SEN, which is not explicitly equivariant, with downstream equivariant networks, and then just train them end to end. So it's a very simple idea. The intuition is that because they're optimized jointly to minimize some loss, the first symmetric embedding network should learn to map the inputs into like some sort of representation so that the equivariant network also minimizes the loss, so that the entire loss is minimized. So in effect, like the downstream equivariant networks provide like the indirect kind of supervision so that the SEN learns to map to an image space where the group action is known, basically. So again, using that example, so the SEN can learn to map the input image into like a top-down view, or it could maybe just be like a low-dimensional feature map where the learned features are symmetric. All right, so in this paper, we kind of focused on world modeling as a concrete instantiation of this idea. So in world modeling, basically high-dimensional image inputs are mapped to low-dimensional representations that are important for latent dynamics modeling. So we propose like a general meta-architecture that consists of the SEN, there's a separate encoder as well, and there's a transition model. So specifically, the state S sub t is passed to the SEN, which gives an intermediate output y, for which the group action is known, and then it's further passed to an equivariant encoder that extracts only the features necessary for latent dynamics modeling. And then the input, so it outputs the latent state z, and then using z and the action, the equivariant transition model predicts the next latent state. And this meta-architecture, it's very general. We tried it on a variety of like domains with different symmetry groups and different tasks in general. And so yeah, these are some of the domains we tried. There's actually 5 domains here, even though I only show 4 columns. So some domains are object-centric, so they're the first 2 columns. These all have 5 objects, and they have permutation symmetries in addition to like rotational symmetry. And then some others have like reflectional symmetry or like 3D rotational symmetry. And like our meta-architecture, it's flexible enough that you can apply it for each of these domains. All right, so here we visualize the learned symmetric embeddings. So the top image for the 3D teapot task, it shows the ground truth where it's rotating, rotating on the vertical axis around the vertical axis, and then the models are trained to reconstruct this kind of trajectory. So we can see that the non-equivariant model in the middle wobbles slightly, and it can't. It's hard to tell, but it's wobbling a little slightly, and then it can't really kind of discern all the different axes of rotation. While our method, it recovers the correct 3D orientation up to like choosing a new frame of reference, and that's always going to be ambiguous. And then here, for the reacher task, we can factor the learned embeddings into different irreducible representations. And then in the reacher domain, so you can see that the middle 2 factors, they show like a clear circular pattern, and this supposedly matches the joint rotations you see. So one large benefit of using SEN for world modeling is that you can train the meta-architecture on a limited number of actions. So you don't need to see all the actions for each state. you just need to see a couple of the actions for every state. And then you can generalize to the full set of actions. So on 3D blocks, you can train only without the left action, so there's only up, right, down, and then you can train on all 4 cardinal directions. And then you can see that SEN achieves higher performance and lower equivariance error than both the non-equivariant or the fully equivariant baselines. And so basically, this work, I would say it makes equivariant networks more applicable in a wider variety of domains, and you can still kind of leverage the benefits of equivariance with this approach, even when the group action isn't known. All right, so I'll move on to kind of the next set of works where we propose different types of equivariance. Basically, so namely correct, incorrect, and extrinsic equivariance, and in collaboration with Yeon Wang, Shupeng Zhu, Neil Sautour, Lawson Wong, and Robert Platt. So these papers were published at Eichler 2023 and NeurIPS 2023. All right, so to begin, there's some fundamental assumptions that an equivariant model takes. So first, it of course assumes that there's an equivariant task function because we're modeling that task function. And then, so the equation shown is like that equivariant constraint onto the function, basically. So second, there's also like an implicit assumption that the data distribution is invariant with respect to the symmetry group. So formally, if you're given a sample X from the data distribution, we expect that the density P of X is equal to the density under the symmetry transformed sample. So, and our work considers what happens if this assumption is broken, and then we propose like different types of equivariance based on that. All right, so I'll explain the different types with a simple example. So consider a classification task where the data points are in R2, and the labels, it's just binary, it's 0, 1. So in the figure, the data points come from a distribution of a circle, and the blue points have the labels 0, and then the orange is label 1. So I'll use circles here to demonstrate like the original samples, and then I'll use X's for like the symmetry transform samples. So correct equivariance is the most common scenario, and that's what we normally consider when we say like equivariance constraint. So it's when the task symmetry matches the model symmetry. So by task symmetry, I mean that the symmetry present in the task, which is like we're trying to learn the function f. So let's say we model the function f with some model that has reflective symmetry across the horizontal axis. And in this case, the original data samples shown in circles are transformed into x's by reflection. And you can see that the labels remain the same, obviously. So meaning that the model symmetry matches the task symmetry. And also the transformed data samples are still in the same circle distribution. Now we define this, so this is a correct equivariance case. And then this is the incorrect equivariance case. So in this scenario, we model the function so that it's equivariant to rotation by pi, let's say. Now in this scenario, the transformed data samples of the x's now have exactly the opposite of the correct labels. And since their labels are reversed, this model can't correctly express the function. And effectively, the model can only perform like a 50% success rate, so it's randomly guessing, basically. Now, again, the transformed data samples are still in distribution, but now the transformed labels conflict with their ground truth labels. And now the third type is extrinsic equivariance. So this is when we relax the assumption for the data distribution. All right, so let's say we model f to be equivariant to scaling. And then in this case, the transformed data samples are now obviously out of distribution of the circle. And then because the transformed samples are out of distribution, there's actually no conflicts in the labels. So in fact, because the model symmetry enforces the original data to be equivariant under scaling, we see like completely new samples. So kind of like data augmentation, which, yeah. All right, so that was extrinsic equivariance. And now this kind of begs the question, is this actually useful? And then why do you want to distinguish between these different types of equivariants? So normally, most people would think, I mean, this kind of extrinsic equivariance constraint would be harmful because it's the incorrect kind of inductive bias. And this would obviously lead to kind of worse models. However, like if you enforce generalization to out-of-distribution data, this can actually make learning the decision boundary easier, and this is kind of easily seen in this example. So if you enforce equivariance to scaling, then you might, because you're kind of showing more samples that show the decision boundary as a vertical axis, then it might make the neural network, might make it easier for the neural network to find that decision boundary. All right, so here are some empirical results. So we actually find that extrinsic equivariance can improve performance quite a bit. So these results were on several robotic manipulation tasks where the observation is some RGBD image. It's captured from a side view, so it's not a top-down view, and there's also like the gripper in the way that obscures some stuff, and then there's a checkerboard pattern that kind of breaks the rotational reflective symmetry. So yeah, so all of these tasks have O2 symmetry. So the, for example, the block picking task, you can place a block anywhere there, and it should be able to learn a policy that's equivariant to that to O2. However, because of the symmetry breaking factors that I mentioned before, now it's kind of extrinsically equivariant. So for the policy, if we use SAC and enforce kind of D4 symmetry, so and you combine it with there's some details here. There's some random crop augmentations, and there's like preloaded expert demonstrations. But basically, the blue line, which is the extrinsic equivariant SAC, you can see that it's a lot more, it learns much more quickly than the other baselines. And sample efficiency is especially important for learning like a policy in reinforcement learning, which is notoriously sample inefficient. Now, this is a simple example. So extrinsic equivariance, I've shown that it can be very helpful, but it can also be harmful as well. So consider the scenario where there's two spirals on different planes. If we use a model with C2 equivariance along the z-axis, then it effectively sees like this, the two spirals together, and this is the classic Swiss roll classification example, which is difficult, known to be difficult. So, I mean, extrinsic equivariance can also be beneficial, but it can also be harmful. In practice, I'll say extrinsic equivariance can get you actually pretty far. So from the previous tasks, we were able to see benefits. So we tried ablating the camera angle, how skewed it is, and then we could see benefits from when it was only 15 degrees off the ground. So it's a very skewed perspective, and it still was better than the non-equivariant model. All right. Okay. So I'll pivot here and talk something a little different. So it's perhaps more relevant for this conference. So in this work with Lawson Wong and Robin Walters, I'll talk about how we can incorporate mesh intrinsic symmetry and for learning PDEs over meshes. All right, so non-Euclidean manifolds embedded in 3D space naturally occur in many domains, so ranging from 3D object modeling, computer vision, structural biology, neuroscience, climate modeling. So such manifolds they're often discretized into meshes to make it more computationally tractable. And while there's other kind of commonly used 3D representations, such as point clouds or voxels, only meshes kind of encode both the geometry and topology of the surface, and they kind of directly represent the manifold. So partial differential equations, or PDEs, they govern the underlying dynamics of many kind of fundamental problems in engineering and science. So in particular, you can modeling PDs over surfaces is very important. Let's say in thermodynamics, aerodynamics, acoustics, material science. So previous kind of machine learning approaches, a lot of them learn signals over meshes and often treat the mesh as like a graph and approximate local patches of the mesh to be Euclidean. And some early approaches used orientation independent features, which loses a lot of the important geometric information. Or you can also choose like a fixed reference frame, which doesn't always work for all manifolds, and it's sometimes ambiguous. And then these, there's been several previous works that have shown that if you don't incorporate the intrinsic geometry of the mesh, then it often leads to reduced performance. All right, so to properly express the geometric kind of information of a manifold, you must consider like the important symmetries of the manifold. And here, so I'll use like a simple example to explain gauge symmetry here. So in the left figure of a very simple mesh, let's focus on vertex B, and then its neighbors. And then, so we're trying to figure out the gauge symmetry for vertex B. And so you project the neighbors onto the tangent plane at vertex B, and then there's clear ambiguity in the choice of local reference or gauge. And so, for example, if you look at the top right figure, if you choose vertex A as the reference neighbor, so now it's on angle 0 basically, you get one set of orientations for the other neighbors. Now, if you choose vertex D as the gauge, and then you see the bottom right figure, so you again get different values. And this is not really what we want, because the network, it should really be independent to the choice of gauge, because the choice of gauge was really arbitrary. You can choose vertex A, you can choose vertex D, it doesn't really matter, but the outputs shouldn't change under this kind of arbitrary choice. So in other words, the network should incorporate this kind of symmetry, and then it should be equivariant to local gauge transformations. All right, so in this work, we propose using nonlinear message passing networks that are aware of the gauge symmetry of the manifold. So I'll first talk about graph neural networks from the lens of message passing, and then talk about like the kind of largely three different flavors of message passing. So in this figure, this is from Michael Bronstein's like manuscript. So in the figure, we're trying to compute the updated features at node B after one round of message passing. Now, so there's three flavors: convolutional, attentional, and just most general message passing. So in the convolutional approach, features from neighboring nodes are multiplied by fixed weights. These aren't learnable. And then aggregated, and then the result and the feature at node B are passed to some kind of locally permutation invariant update function. Now this is basically equivalent to a linear combination of neighboring node features, and thus the messages passed from the neighbors are just linear. In the attentional flavor, there's a attention mechanism that computes the interaction between the neighboring node and the source node, which is node B. And then after the attention is computed, then it's then aggregated to be passed to the update function. Now the weights here are learnable, and now they can depend on the neighboring node features. Now lastly, in the most general case, the message passing flavor, a message function M, which is possibly nonlinear, is learned on both the source and target nodes, so on the edges. And then the outputs are aggregated and passed to the update function. So this is kind of the most general approach and encompasses both the convolutional and attentional approaches, and it can compute nonlinear messages from the neighboring nodes. So analogously to how there are largely kind of three flavors of message passing in graph neural networks, you can consider three flavors of gauge equivariant message passing networks. So although previous work on gauge equivariant networks for meshes, there have been convolutional attentional approaches. So we find that they actually underperform when you're trying to model complex dynamics over meshes. So kind of this connects to the PDEs over meshes that I talked about earlier. So we introduced like a new architecture, Hermes, that combines gauge equivariance with nonlinear message passing. And it demonstrates improved performance on surface PDEs and other complex dynamics. And it kind of completes the full picture for the 3 flavors of message passing, gauge equivariant message passing. Okay, so here we show an instantiation of our architecture for one of the surface PDE datasets. It's shown for like this simplified 4-node example from before. The message function is depicted as the edge network on the bottom left. And then it takes in neighboring node features and then possibly edge features. So after an aggregation step, the update function, or here on the bottom right, the node network, it takes in the outputs computed by the edge network and its source node features, and finally computes like the updated node features. So a key point to note here is that we effectively decouple the network depth with the receptive field of the graph. So in a convolutional approach, the receptive field, how many hops away it gets messages from the neighbors, it's directly tied to how many graph convolutions layers you have. But here you can arbitrarily make it as large as you want because the edge network, you can design it with however many layers you want. Now, because our architecture can compute messages using features that are like an arbitrary hop distance away, the hypothesis is that this decoupling is very beneficial in tasks with complicated kind of interactions. Okay, so we evaluate our method on several different domains, such as surface PDEs, cloth dynamics, object interactions, and also shape correspondence as well. So for the PDEs, we consider the heat equation, wave equation, and Cahn-Hilliard equation. So these are all very basic equations. The Cahn-Hilliard equations, it's a little different, but it describes phase separation in like a binary fluid mixture, and it's a complex kind of 4th order nonlinear PDE. Again, so these were kind of the examples that I could find and generate data for. I'm not like a PDE expert by any means. So yeah, we consider these 3 PDEs. We also test generalization to several different scenarios. So for, we consider generalization to future time steps with test time here, different initial conditions, and then unseen meshes. So this is test mesh here. All right, so in our experiments, we found that Hermes, our architecture, it outperforms convolutional and attentional counterparts pretty significantly. And it outperforms other graph and mesh baselines. That's shown on the right, so GCN, NPN, and spiral net, so forth. There's mesh graph nets here, and it performs actually pretty well, but Hermes is still out on the top. So I want to highlight that, in particular, Hermes performs the best on the test mesh datasets, so the unseen mesh datasets. So this suggests that kind of Hermes is able to better learn the true dynamics function rather than instances of the PDE. And so that means that it doesn't overfit to specific kind of mesh geometries. And it really models like the true PDE function. I wasn't sure how well this would work. Okay, so, they're supposed to start at the same time, but anyway. Okay, so here we visualize kind of qualitative samples from each method when the predictions are rolled out for 50 time steps auto-regressively, given only the initial conditions. So on the heat data set, which is the top row, we see that GEM-CNN, this is the convolutional gauge equivariant message passing flavor, and it diverges quickly. Like it diverges quickly. It's just it's pretty bad at the autoregressive predictions. and Eman and Hermes, Eman is the attentional flavor. So Eman and Hermes, they can generate rollouts pretty close to the ground truth, which is shown on the far right column. On Conn-Hilliard PD, so we can see that GEM-CNN has high errors, and Eman actually diverges here. So Hermes, for all of the PDEs we considered, it doesn't diverge, and it gives fairly realistic rollouts here. All right, so that's actually the end of the talk. I'd like to thank all of our collaborators, and yeah, thank you for your attention. Yeah, it seems like kind of ended early.
So people never angry at the end early. Hey,
Yeah, please, if you have any questions, feel free to ask, like me or Robin. Yeah. Yes.
Oh, sorry. I was hoping to ask about the extrinsic
yeah,
equivariance
sure.
problem. So you have this problem, for instance, that has a set of the robot tasks.
Oh, yeah. Yeah.
Can you give an example of what happens if you don't include this extrinsic? What
Right.
in a physical sense, what do you gain?
Right, that's a very good question, and I probably should have spent a little more time here. So the idea is you're trying to learn some policy, so given the state, you want the actions output from that policy to be consistent. So in all these tasks, you're picking up a block in some position, and then the action in order to pick up that block is, let's say, that's the policy, but if you rotate that image, there's a relation between the action that you did for that original position and the rotated position. And because of that kind of equivariance constraint, so it actually decreases the number of samples you need in order to learn that policy. Now, if you don't include any kind of equivariance constraint, then you need to see that sample in that kind of rotated position, and then you have to, again, use more samples to learn the correct policy for that. But if you relate it in this way, now it decreases the sample, it increases the sample efficiency a lot. So you don't need as many samples. That's why there's like a big gap in the graphs here. And then that, again, applies for kind of the extrinsic equivariance constraint because it effectively acts as like data augmentation kind of process. And yeah, does that answer your question?
Yeah, I think so. Thank you very much.
Okay.
I'll have to rotate it in my mind a little bit.
Okay.
But.
you gain efficiency, but you also in some cases, so the reward, the y-axis here is like some indirect measure of how successfully it's completing the task. The x-axis is how long it's trained for. So when the blue line shoots up a lot faster than the other lines, it's learning faster or more efficiently, so that's what you gain. But when at the very end, at the far right of the plot, when the blue line is still higher than the other lines, especially if it doesn't look like they're going up anymore, then it sort of shows that there's even like a gap in the ultimate like converged policy, which means that you actually have a more accurate, effective policy by virtue of sort of the symmetry of the model.
Yeah, these are analogous to the kind of training curves you would see for neural networks. Yes.
I'm curious what inspired you to study extrinsic equivariance from the get-go, because a priori I would have thought either you have symmetry or you don't. And the surprising result here is that if you can sort of, I don't want to say fake the symmetry, but you just choosing any kind of symmetry helps. So what inspired you to come up with this third theory of extrinsic
Yeah, that's
equivariance?
a great question. There's kind of a story for that. So the first kind of paper that I talked about here, so we have a non-equivariant baseline, and then we have kind of our hybrid baseline. And then we have a fully equivariant architecture. So this one is like, again, even if it's a skewed image, you just, still apply equivariant neural networks. And then we actually found in our experiments it performs surprisingly well. And that kind of motivated us to, study why does it work very well. And then that's kind of where we proposed defined the different types of equivariance. And that's exactly, the fully equivariant baseline is based exactly like the extrinsic equivariant scenario.
Interesting. So it's kind of like you stumbled on the result, and then you were like, you sort of went further. It's like, let's see if this generalizes, and it did.
Yeah, and then I guess we had to also come up with like the definitions, and then like what's different about it. Yeah, so one kind of maybe something that's a little unsatisfying is we didn't come up with so even though we defined extrinsic equivariance and distinguished between the different types, there's no kind of measure of how extrinsically equivariant it is. I mean, you could measure the skew of the camera angle, but this doesn't apply to all data types and stuff like that. So that's, I guess, maybe direction for possible future work. Yeah, because, I mean, I've been working in this kind of symmetry and equivariance space. It kind of ties together, maybe. So, yeah.
I think an interpretability study would be interesting as well, where you looked at like the hidden activations for successful and unsuccessful temp for the extrinsic ones. See how it compares to the fully.
That's a great point. I mean, for the kind of harmful scenario, we came with a conceptual, simple kind of Swiss roll example. There's I didn't include it in the slides here, but there's like an empirical result where it's also harmful as well. Again, it's related to robotic manipulation.
My take, if you don't mind, is like whenever you're like taking this approach of like this adding an inductive bias to a model, right, or like adding constraints to a model, there's always like I think like a natural like question that you ought to ask is like how risky that assumption is. Mm-hmm. Because in the real world with real data, your assumptions are usually, I would say, somewhat violated, like a little bit, right? Uh-huh. So it's like if I impose some constraint on the model and I've taken a risk because there'll be some error, which is really like what the extrinsicness is kind of measuring, like how like off was my assumption. And then, like, does my model sort of fail gracefully as the assumption gets violated, or does it just completely fall apart if my assumptions are not all strictly satisfied? So that's kind of, I think, partially where this sort of comes out. And the real, like, I think, sort of, like, tagline is, like, they fail extremely gracefully. In fact, like somehow, surprisingly, they keep working long after, like, they ought to have stopped being helpful.
Thank you again, both. That was a really great talk.
Yeah, are there any other questions?
Yeah, I don't know. Maybe mine's a little more basic, just on this one. So like,
on this one.
Yeah, I was like, so if we go back to like the block pushing example,
Yeah.
or maybe I should rewind back, and like I think I wasn't exactly clear what like the exact definition of like extrinsic equivariance was. It seemed like it's you impose some sort of additional group action or symmetry that like pushes your data like out of sort of like the real world distribution that you see, and you ask for equivariance under that additional group action.
Yeah.
So in the block pushing example, what is the group action and what is the like additional extrinsic? I heard you reference like O2, and I was like, not sure what you mean by that. And so if you could just clarify.
Yeah, here, actually, so since we have the images, I can use the images as an example. So the actual task has O2 symmetry, but we impose D4 on the model. So like I guess it's a discretized kind of approach to the full O2 symmetry. So here, if we look at the first kind of block pulling example, so this is like the state you see. If you impose D4 symmetry, the idea is you exactly rotate the image, just assuming that it's a top-down view and assuming that it's a perfectly rotationally symmetric.
Sorry, could I ask by D4 you mean like the dihedral group on 4 elements?
So
or, okay.
Yeah.
Okay.
There's
8 elements,
it's the cyclic kind of group with C4, but with reflections as well.
Okay.
Yeah.
Okay.
So 90-degree rotations and a reflection.
And the input is like the camera shot,
Yes,
or is it
exactly.
is it top down so that you're looking at the blocks
So
from above?
These are
so
the
that
exact kind of images that you see.
Okay.
So it's a little skewed. You see the gripper, the robot gripper in the image, which so if you rotate it, the gripper comes from the side, which doesn't happen, right? It's, you never see that kind of image in your data set. And then the checkerboard pattern is also, it's supposed to be static, but if you rotate it, now it's not the correct pattern. Like you, for this example, the white is on top of the blue, but if you rotate it 90 degrees, now blue is on top of white, and there's some kind of symmetry breaking factors here if you impose D4 symmetry. And that's why it's extrinsically equivariant.
Okay.
The model wants you to have a top-down view. So like we actually like use, like in our past works, we would engineer this kind of top-down, perfect top-down view, right? We like basically like process the, we have like in the real robotics experiments, we use like a 3-camera depth camera setup where we like register everything and synthesize the top-down view. No gripper, no like obstructions, no background, perfect like top-down view. So now when you rotate that image, rotating that image exactly corresponds to rotating the blocks. So it's going to exactly like the symmetry in the like the vision model, that's just like image rotation, exactly lines up with the physical transformation of the space. So the policy is perfect, right? But then like, you know, what if you just like actually want to like stick just one RGB camera there and try to use that for your observations? You can't stick it exactly top down because the gripper keeps getting, the robot keeps getting in the way. So people usually put it a little off to the side, right? So now you have that gap, right, between the perfect top-down view you want to have and this like slightly skewed image, you know what I mean, with like, sees the gripper even though the gripper arm's not correctly, like when you rotate the world, the arm moves, but that's not the rotation that the model is supposed to be generalizing from. There's like just things, distractors, like this like background coloration, that's not relevant to like rotating the system state. So all of that is part of this sort of extrinsicness. Stuff that like rotates that isn't supposed to be part of the state.
I will say the robot gripper, like in the image, that's a very common example, and it's not really mitigated by however many cameras you have, because, like, let's say you're close to the object, you almost picked it up, but you know it's still obviously going to be in the image, their camera.
Okay. Maybe just the last thing. So, like, do you build in equivariance to these kind of like, I don't know, these sort of like out of distribution factors, I suppose? Like, or what was the, how is it that you achieved like the equivariance to this, or was it not a change to the network? It was just sort of noting that it can handle these things, or?
Yeah, there's different solutions to this problem. So like this is related, by the way, extrinsic equivariance is like our name for it. It's from, like for the mathematical, like, but like in the physical example would be like symmetry breaking in inputs that are sort of missing from the model specifications. So like basically you have symmetry breaking factors you're trying to cope with here. And in this approach for this paper, what we did to address this complicated problem was nothing. Right? Like we basically pretended that it wasn't there and saw how the model did with it, right? And the sort of like math that John showed some of, but there's actually like some theoretical results in the paper, sort of say that like in the extrinsic case, in this like where it's not extrinsic but not incorrect, there are these two cases. If the symmetry breaking factors in your environment lead to this incorrect scenario, then the equivariant model will have to suffer. But if it's extrinsic, then you kind of don't know. It doesn't have to produce errors. And so you might as well try and see what happens. And the result is and the result is it can either help or hurt. And in these robotic manipulation cases, it helps. In some cases, like that Swiss roll example that John showed, it hurts. So there's no like sort of, it's not forced to help or hurt. Now you can do, in other follow-up work, we've worked on models that are relaxed equivariant models or equivariant models with symmetry breaking. And these are models that can explicitly try to like infer and learn the sort of like symmetry breaking or extrinsic elements in the domain. So you can kind of like factor them out to get better performance. So that's another approach to this problem.
Great, thanks.
All right, are there any other questions?
Yeah, so I mean, I figure we could sort of start the, people can ask questions offline.
Yeah.
So we certainly encourage people to do that. I think there should be snacks outside, at least in 5 minutes, I guess. But we can sort of break a little early. And the next talk will start at 11.